Hey Darts fans, that's Timo Newman here, the transporter. Welcome to the good ship Undarted Waters, and finally, we are beginning this long, perhaps perilous voyage. It's something that I've been mentioning for the last so many weeks, and even in my last video I said, oh, tomorrow or the day after we'll start, and it's now like 4 or 5 days later because it's been really hard to get everything prepared to set sail. You know, get the provisions on board and get the crew ready and everything. And you know what? We're still not ready, but we're going to set sail anyway. The captain, namely myself, has decided enough procrastination. You can't have everything perfect. We're just going to set sail. What is this voyage? This voyage is about what happens between the dart leaving your hand and hitting the board. So call that what you will, the trajectory of a dart, the flight path of a dart, the dynamics of the dart, the physics of the dart, all of those are good descriptions. But that is what we're going to be talking about. So why are we going to talk about this? Why are we going on this voyage? And I hope that you'll stay with me for this whole voyage. I don't know how many videos it will be. Could be 4 or 5, it might be a lot more. I just don't know, because it sort of depends on interest, and it depends how deep you really want to get into this, because you could write a PhD thesis on this topic easily. It's very deep, and that's why I've spent so long trying to get everything sort of prepared in a way that I think is fit for purpose. Why would we talk about this? Well, first of all, of course, it's just because human beings are intelligent organisms and we're curious. We'd like to know about things. You know, curiosity is often the catalyst for great science. It's like, well, what does happen to that dart between leaving our hand and hitting the board? And that's the whole physics of projectiles. But really what motivates me is a bit more than that. It's more than the physics of the projectile. It's more about, if we really understand this in detail, and if we understand how it changes from person to person, this is really important, can we then learn for us as each individual uniquely what is the physics of the dart telling me that I can use to be better? Because I believe that when we make predictions from all this, because I'm not just going to be using words here, I'm going to do some maths as well. We're going to make predictions about what happens when the dart leaves your hand. We can actually reverse engineer that then and say, how can we as an individual hone and perfect our throw for each different target on the board? Because when I say the dart hitting the board, where on the board? Because we all know this, I'm sure we all feel this when we throw darts, that there are some heights of the dart that are very comfortable. For me, the bull and the treble 20 are very comfortable. But for me, going down to, say, the treble 19 or the double top takes quite a big readjustment. And we just do this by feel, by practice, hours and hours of practice, and we feel this difference. But it must be reflected in the physics. And that's what I want to get at with this. And I haven't quite got there yet, but I know I will. And by the end of this voyage, whenever that's going to be, in a week or two's time, I will have it and I will tell you about it. I'm very, very close. But I didn't want to keep putting this off until I had everything ready. Like I say, I want to just get started. So that's a nice little, what do they call, what's that? That's 126, isn't it? The 126 checkout. You see that quite a lot. I love checkouts where you have to move around the board like that, sort of ending on the bull particularly. They're really, really special. So in this first video today then, I've just kind of tried to motivate a little bit, and we'll get more motivation as we go on. But the two things I want to talk about today are setting up the problem as a physicist would, so you can see how does a physicist set this up that you can actually analyze it. And then secondly, I want to just describe what the forces are that will be essentially responsible for that trajectory. So let me get the whiteboard. Let's turn the board light off. So here is the kind of the framework. This is the framework for this this voyage. Okay. So should be relatively self-explanatory. Here's the dartboard, and we know that the bull of the dartboard is at the regulation height, which in imperial units is 5'8", and I tend to be very fond of old traditional units, but you know, folks away from the UK will know what that is in centimeters and so on. Here's the oche. This dart player is legal. They've got their foot behind the oche, and I've tried to draw it reasonably to scale here, not in the horizontal direction. It would be this chap would be a bit further away, but height-wise, it looks well. Actually, it's quite a tall person, right? Because the eye level. This is actually a very tall player, but never mind. Reasonably to scale. And we're catching them at the very instant the dart leaves their hand. Okay, so we're not talking about the physics of the action, but at the moment, at that instant, that microsecond, the dart leaves the hand, is when this photograph was taken of this matchstick figure. And a key thing will be the height of the elbow above the ground, and very important will be the relative heights of the target. So that's the bull in the middle of the board, but there's a target that looks like they're aiming for treble 20. Surprise, surprise. Even in matchstick darts, a 180 is the best score. So you've got the height of the target. Let me actually write in here then. I'm going to call that H with a little t next to it. That's height of target. And then over here, I'm going to write this as height of elbow. All right. And then we've got this horizontal distance, which is at the point of release, where is the elbow horizontally from the board? Okay. And I've just realized that this has to be from the board. So let me just make that absolutely correct there. So there we are, from the board. And we're just going to call this D for distance. I'm using symbols that are very common in physics. So we often use D as like a horizontal kind of symbol, and H obviously for height. All right. But something I want you to already notice here is that for the target, let's say it's treble 20, that's going to be the same for every player. However, the height of the elbow and the horizontal distance of the elbow from the board will be unique for every player. Unique. So for me, for yourself, for Gerwyn Price, I don't know why I often mention Gerwyn Price. I don't know. I'm very fond of him as an elite player. He's got such a brilliant competitive spirit, and he's so blooming good as well. I mean, really, really good. When he's on his game, he's almost unbeatable, except, as we saw recently, Luke Littler. Wow, what a match that was. Incredible. But anyway, yeah, so every player is going to have a unique height of elbow and horizontal distance of elbow from the board, okay? So that's some of the geometry. It's the point of release of the dart. This dart is going to trace out some trajectory, and this is a very good player. They've actually hit their target, okay? And that green line is a bit shallow because the board's not really high enough, but it's a relatively accurate line actually for reasons that we'll get into as we go along with this voyage. So why is there a piece of paper stuck here? I want to just zoom in on the action, on the elbow and the darts, because I need a couple of more things before I can define all the parameters I need to describe this problem. So let's just take this piece of paper off. The reason it's covered up is I taught for many, many years science in universities, and I know as a student too, when I used to go to lectures, actually I didn't really go to many lectures because often they weren't, I didn't find them very helpful. But what I know is that if someone presents you with a really complicated diagram, you just switch off. So I know you've got to build it up step by step and lead people through without just making them just zone out right at the start. So I know that if I had all of this on the board when you first looked at it, it would be harder to follow what's going on. But we're zooming in on the elbow. Right. Let's just put that piece of paper there. So this is a slightly magnified view of the elbow. So that's this arm is here. There's the dart, and there's 3 more parameters we need. Because you might be saying, well, why do I care about the height of the elbow? Surely I care about the height of where the dart's released. Well, that's true, but I want to try and set this up in a way that we can really use it. Okay, because if you ask me about the height of the dart when I release it, I don't really know, but I do know where my elbow is. And you can get a friend or a family member to measure the height of your elbow when you throw, and to measure where the elbow is relative to, say, the oki, measure that distance and take it away from the oki distance. And you can get these numbers for yourself, and I really encourage you to do that, okay? So the elbow is a fulcrum in the physics point of view, and this forearm and hand is like a lever, and that's really important now. So we need this distance of the lever, and as the dart is released, essentially, let's keep that elbow fixed, and you've got this motion. We want to know the length of the lever, and I'm going to call that L. Okay, and that's just another common symbol that we use for length in physics, L, for the length of the lever. That's the distance from the tip of my elbow to the dart in my hand. So for me, that's 16.5 inches, okay? Now, that we need two more things, and then we have everything we need to know in terms of the geometry and setting up this problem. This dart is going to, when it's released, is going to go in a trajectory, and at first it will be relatively straight. So just after it's released, it will move in a straight line, and that defines what we call the velocity. So the velocity in physics is not something like 30 miles an hour. That's what we call a speed. But a velocity is something that has a size, which is the speed, but it has a direction. Okay? So, well, I won't say more than that right now. So it has a direction as well as a size. The size is the speed. So that dart is going to be released with a certain speed, and we're going to call that speed of the dart small u. And that's another very common symbol in physics to describe speed, okay? And you can see I've drawn in these angles here. We need to know what is that direction of the dart, and that allows us then, with that direction and with the speed, to talk about the velocity, okay? And I'm going to use one unfamiliar symbol here for some folks. Others may have seen this symbol in maths and in physics. If you need a symbol for an angle and you haven't already used that symbol, everyone uses the same symbol, and it's a Greek letter, and it is the Greek letter theta, which looks like that. And you may have seen that symbol at school, or you may have seen it in other places. So theta, that's that angle. All right. So that, but the way I've drawn it here, it looks like it's about 30 degrees. Okay, it's quite shallow, to be honest. I think what we'll find when we do these calculations is that the release of a dart tends to be more around 40 degrees. Has quite a loftier trajectory, not so shallow. Okay. And what we also need to know is this angle here, because we need to know the angle of the lever when the dart is released. Unfortunately, we can just do a little bit of simple geometry here. You'll all remember that the the angles inside a triangle have to add up to 180 degrees. And if you have what's called a right angle triangle, one of those angles is defined to be 90 degrees. So the other two angles have to add up to 90 degrees, because 90 plus 90 is 180. So you can see here that I've got a right angle triangle essentially. Okay, so let's see. How do I want to think about this? Yeah, so this angle here has to be, this is a right angle, so this angle here has to be 90 minus that one, so that's 90 degrees minus theta. This is a right angle, so for this triangle, this must be theta, because then theta plus 90 minus theta plus 90 is 180 degrees. So I'm looking at that lower right angle triangle, and then there's this right angle here. So just from some simple geometry, very happily, we don't have to define two angles. This also is theta. And that's really, really helpful. So those two angles are the same. Okay. So we only have to worry about one angle, and it's the angle of release. Now you might say, well, I don't know what the angle of release is when I let go of my dart, and you're absolutely right, neither do I. I mean, you could film yourself and kind of stop the film just as the dart is released and measure it, but that's not very useful for when you're playing. And so the speed at which you release the dart and the angle of release are things that we actually want to keep general at this point. Okay, so those are not parameters, those are what we call variables. Those are going to take different values, because as you're aiming for different targets on the board, as you know from experience, if I go for bull versus going for double 20, I know I'm going to have more speed given to the dart. And the angle too will be slightly different, quite possibly. So that combination of speed and angle will vary as you go for different targets on the dartboard. Okay. So let's just make a quick list then of the things, all the things we need in setting up this problem. We have the height of the target, which is just something that's going to be the same for everyone. And you can just decide what target that is, you know, oh, it's going to be the bull, or it's going to be, you know, double 19 or whatever. We've got the height of the elbow for a given player, which their friend or family member can measure for them. We've got the distance horizontally of the elbow from the board. Again, friend or family member can measure for them. We have the length of their lever, so from the tip of the elbow to the dart, friend or family member. And then we have these other two things, which are, so these are really parameters, and then we have the initial speed and the angle of release are these two variables that will appear in the equations as things that we want to just keep general at this point, okay? Right, so we have set up the problem. From a physics point of view, there's no more inputs that we need other than that. Okay, so what we're going to do in the next few videos is just see how would a physicist solve now for this. But what you'll find is that this is actually quite a difficult problem. Right. Why is it a difficult problem? It's, you know, if you do a degree in physics, if you do an undergraduate degree in physics, at some point early on, you will be taught how to calculate the trajectory of a projectile, like a cannonball, something like that. And what's nice about a cannon is that as you change the angle of the cannon, where the cannonball starts at the bottom of the cannon doesn't really change very much. But you see, what's different about this is that the point of release of the dart depends on this angle theta. So you might release the dart earlier, or you might release the dart later. And so the starting position of the dart depends on this angle theta, and that will be something that changes for different targets. Okay, that is a little wrinkle in this that actually makes it really a right royal pain. If it weren't for that, I would have had all of this done quite some time ago, but it's really a wrinkle. We can deal with it, but it's painful, and I won't drag you through all that pain, but I will show you why it's painful, and I'll show you the results. And just in general, the approach that we're going to take in these next few videos, I'm not going to go through all of the maths and all of the gory details, because there's not really much point to that. If anyone's really interested, I can do that, but I think generally what folks would like to know is what's the physics of it, what's the concepts behind it, how would you go about solving it, and then what are the results? And when we have the results, those are like predictions, and then can we tailor those to individuals, and then can individuals learn something from those results that's really going to help their game? And that's the ultimate aim of this. And what I'm hoping to do by the end of this series is not only look at my own parameters, but take these parameters from different players like Luke Littler or Gerwin Price or James Wade, you know, take your pick. We can use the images and videos of players that are available online, get very good estimates of these parameters, and see, well, what's their personal profile on how they manage the things that vary, the speed and the angle at the point of release for various targets. So each player in the end is going to have like a personalized kind of like signature of how they throw the dart according to the physics of how a dart moves. Okay, and it's something that you can actually change if you wish, because if you change your stance, these parameters will change. Okay, so before we end this introductory video today, let me just say something then about the forces. So the forces are the things that operate on the dart after it's left your hand. Now, the instant that dart has left your hand, you have no more influence over it. Okay, I know people talk about follow through. That's very important, but it won't affect the dart. I think the point of follow through is that it's because you know you're going to follow through, that will make your throw more fluid, more smooth. Okay, but when the dart leaves your hand at that instant, whatever you do with your hand will have no influence on the dart whatsoever. As soon as the dart leaves your hand, there are two forces that act on it, and those forces completely determine what happens to the dart afterwards. What's the first force? The first and the most important force by far is gravity. And gravity is one of the four fundamental forces of nature. Any two masses in the universe will feel each other through gravitational interactions and tug on each other. Okay, and so this dart, once it leaves your hand, let's say we look at the dart when it's here. Where's that other pen? In mid-flight. Let's ignore the fact that the flight of the dart has changed colour, never mind. But there will be a force on that dart which is vertically downwards, and that is the force of gravity. Okay, and the size of that force is described in terms of something we call small g. Okay, and that is the force per unit mass that acts. Okay, and you might have heard of G for Earth is 9.8 meters per second. For reasons we'll get into in the next video, that force per unit mass has dimensions of acceleration, and that's often called the acceleration due to gravity, and it's 9.81 meters per second. And that's going to be pulling that dart down, and that's why the dart goes through the trajectory that it goes through, pretty much. But that's not the only force that's acting. The other thing that's happening to that dart is that it has to push its way through a fluid. We're not playing darts underwater, but we're playing darts in air, and in physics, air is a fluid. It's a very low density fluid, but it is a fluid. And air resistance is very important You know, if you are a parachutist and you jump out of an airplane, you're relying on air resistance to save your life. First of all, the air resistance will mean that you have a terminal speed. Terminal's an unfortunate word to use, isn't it, with parachute? Sorry. But that's the technical word for it. But when you jump out of an airplane, I've never done this, by the way, I never will, but you accelerate under gravity, but then the air resistance builds up because it's a stronger force as you move faster, and at some point it will balance the force due to gravity, and your speed will just become constant. That's called the terminal speed. And then when you open your parachute, that's designed to have a much larger surface area. The air resistance gets hugely greater, and then you will massively have a much greater force from air resistance, and that will slow you down even more. Okay. So air resistance is really important, and it operates against the direction of travel. So the direction of air resistance as a force is like this, okay? And that's, let's just call it air resistance. Okay. Now the problem with air resistance is that, as opposed to gravity, which is really, really simple to physically describe in the equations, air resistance is not. And that's why you could do a PhD on this problem, because if you wanted to really take into account air resistance properly in every last minutiae, you would need a supercomputer and you would need a whole team of people, because the way that objects move through a fluid, whether it be air or water or whatever, is extraordinarily complicated. Okay, that's the whole field of fluid mechanics and hydrodynamics, and they've been very active fields for 200 years, and there's still many mysteries in those subjects. Okay, so there are simplified forms that you can write down for air resistance, and that is what we will use. That they are the very tried and tested, and we will use something called Newton drag to describe air resistance, and I think that is the appropriate thing to use for a dart moving through air. So that's the end of our introduction. If there were no forces acting on the dart, it would move in a straight line. And that is how darts would be played in outer space, away from any like large planets or stars where there's hardly any gravitational fields. There'd be no forces at all. You're in a vacuum, there's no gravity, so the dart would just move in a straight line. As soon as you add gravity, we have these beautiful trajectories, okay? So if you played on Earth with the gravitational field pulling the dart down, but you were in a vacuum, hopefully you'd have an oxygen tank strapped to your back so you could still breathe, your dart would move in a very symmetrical way. And we're going to look at that in a lot of detail, because that is the basic trajectory. But then when you let air into that sort of environment, and you've got air resistance as well, things get a lot more complicated, and I'm not going to drag you through all that mess. But we will have to take that into account in this analysis behind the scenes to have a useful way of talking about how a dart moves, so that we can tailor it to each individual player. Right, so phew, that's the geometry and the forces. Please give me feedback if you wish on this first video, things that you might be hoping to learn from this series about the physics of dart flight. Okay, and what we'll do in the next video is just have a quick look at darts in outer space, because already it turns out to be a little bit tricky because of this difficulty that depending on the angle of when you release the dart, that changes the starting position of the dart, so it's awkward. So with that then, hope you're all doing well. Sorry for the long delay in getting this series started. 3 darts at the Oki, make them count, even on the moon, and I'll see you next time.